Now let us see the relationship between analog and digital poles in case of impulse invariant transformation. We have obtained the relation, right? Omega, analog omega is equal to omega by t, digital omega by t. How this relationship is obtained between analog and digital poles? That is what we are going to see now. Relation between analog and digital poles. Okay. We know that in analog, S is equal to Pi is an analog pole. We have taken S is equal to Pi. Likewise, if you simplify this, digital pole can be written as Z is equal to e power Pit. This is the digital pole. This is analog pole and digital pole. If we equate this to 0 and find what is Z, digital pole is e power Pit. And also, since S is equal to Pi, what can now be done is, it can be expressed e power St. Z can be expressed in terms of S. Since S is equal to Pi, this Pi can be replaced as S. And always we know that any point in S plane can be represented as sigma plus j omega. That omega is the analog frequency. So instead of this S, we can replace sigma plus j omega into t. And polar form, we can write this as r e power j theta form. So this is the real part, e power sigma t is the real part, and this is the imaginary part. Real and imaginary part they have represented. Likewise, Z is nothing but, it is a complex plane. Z plane is a complex plane which can be expressed as r e power j omega. Where omega here is the digital frequency. Since it is related with Z plane, it is the digital frequency. So we know that Z can be expressed as r e power j omega. So instead of this Z, we can replace r e power j omega. So r e power j omega is equal to e power sigma t e power j omega t. We have obtained the relation between the Z and the S plane. Right? If we equate the real and the imaginary part, real part on both sides, here we have R and here it is e power sigma t. Mod Z is R, which is e power sigma t. If we equate the imaginary part, we can say that omega is equal to omega t. Omega is equal to omega t. Now from this relation only we have obtained the relationship between analog frequency and digital frequency of impulse invariant. So in impulse invariant technique, the relation between analog and digital frequency is this. Omega is equal to omega t, or I can write omega, analog omega is equal to digital omega by capital T. And this relation, if we consider this relation, I can say that this relation of analog and digital frequency in impulse invariant is linear. We will get a linear relationship between analog and digital frequency in case of IIT, impulse invariant. But this will not be the case for bilinear transformation. There exists a non-linear relationship between analog frequency and digital frequency. And that non-linear relationship will end up in a distortion which is called as warping. You might have come across this term in your question paper, second internal assessment. What is warping? How it can be avoided? It can be avoided by using a technique called pre-warping. The reason is, if I take analog to, if I consider the relationship between analog and digital frequency in impulse invariant, it is linear. Whereas in bilinear transformation, this relation between analog and digital frequency will be non-linear, and this non-linearity will introduce a distortion which is called as warping. Okay, that term is called as warping. Okay. Now we have arrived at the relationship between analog and digital frequencies. How will be the relation between analog and digital poles? How will be the mapping between this analog and digital poles in case of impulse invariant transformation? By considering this equation, if sigma is less than 0, in the S plane, I can say that when sigma is less than 0, it gets mapped in the left off of the S plane. S plane la left off la the map out if sigma is less than 0. And if at all I substitute sigma to be less than 0 here, I will get the value of Z to be less than 1. In the negative value inga pottingalum Z oda value enna irukum less than 1 irukum. So I can say that in Z plane, this particular pole gets mapped within the unit circle, inside the unit circle, the shading. So when sigma is less than 0 in the S-plane, we are getting the pole to be mapped in the left half. Its corresponding pole in the Z-plane, this is S and this is Z, gets mapped into the unit circle. We can see this. From this relation, we can justify that particular pole mapping between S and Z plane. How this is getting mapped into the unit circle. The justification is with respect to this equation. Likewise, whenever I consider sigma to be equal to 0, when sigma is equal to 0, in the S plane, it gets mapped on the imaginary axis. It will get mapped on the imaginary axis. For the same case, how will be the mapping in the Z plane? When I substitute sigma to be equal to 0, this is e power 0, which is equal to 1. So I can say that its corresponding pole will be mapped on the unit circle. Since mod Z is equal to 1 for this case, equal to 1, then so it gets mapped on the unit circle in the Z plane. All poles on the axis gets mapped onto the unit circle in the Z plane. Likewise, if we take sigma to be greater than 0, in the S plane it gets mapped in the right off. S plane it gets mapped in the right off. Its corresponding pole in the Z plane, where it will get mapped whenever sigma is greater than 0, this magnitude Z. Whatever may be the value, positive value you give for sigma here and find its e power value, you will get to be greater than 1. So I can say when sigma is greater than 0, the pole which is being located in the left half of the S plane will get mapped outside the unit circle. That is why it is being represented outside the unit circle as strips like this. Okay. This is the relationship between analog and digital frequency and analog and digital poles for impulse invariant transformation. Only from this relation, we are getting the formula. Formula நம்ம யூஸ் பண்ணோம் இல்லையா, analog given the digital frequency in the specification, first of all we have to convert it into analog frequency, only then we can proceed. So this relationship for IIT based on transformation, we will be using two different formulas, right? This is how we have arrived at that particular formula from this relation only. Okay, hope it's clear to you. So the main drawback in IIT is you will get aliasing. Since we are employing a technique called sampling to convert HA of T into H of M, definitely there will be aliasing. And one more thing to be noted here is this impulse invariant is called many to one mapping. Many to one mapping. This is also a drawback here. That is a strip of poles in the left top may get mapped onto the same point within the unit circle. That is called many to one mapping. Strip of now or a set of poles may get mapped to a single point in the Z plane. Likewise, a strip of poles located in the right half may get mapped into some single point in the Z plane. So here many poles from this S plane, it may get mapped into a single point, a single location on the Z plane. That is called as many to one mapping. These are the two drawbacks in IIT. Whereas these two drawbacks you can overcome in bilinear transformation. There you will get one-to-one mapping, and also you will not get any aliasing problem because we will not be going to make use of the technique called sampling. And in this IIT, in order to avoid aliasing, you have to choose a very high sampling period. And practically, we cannot design a filter which is completely band limited. Aliasing avoid pananona, you have to initially band limit the signal. There should not be any high frequencies, right? Aliasing occurs because of overlapping of high frequency over low frequency, is it not? So all high frequencies will be removed. Appa signal band limit panni da nam anupunom, but practical cases la the band limiting cannot be done perfectly. So always IIT will be associated with this aliasing problems at times. That is the main drawback. The other drawback is many to one. Many poles on the S plane can be mapped into a single point on the Z plane.